Good afternoon. I would like to thank the organizers to give me the opportunity to introduce you some part of my recent work. And today I'm going to speak about the integral quantization of Oppenheimer-Snyder model of massive star. The presented results were developed in cooperation with Andrzej Buś, Włodzimierz Piechowski and Jan Ostrowski, and were published in the following two papers. Okay, the motivation which brings us to develop this quantization method based on the need of some effective method of quantization of space-time with gravitational model with spherical symmetric space-time. In such a model, the interesting characteristics does not depend on angles, so the configuration space can be reduced to the following one, where t and r are time and radial coordinates respectively. The schematic description of our quantization method can be explained in such a way that we start from some configuration space, which consists of time and r. We have some set of observables, classical observables, which are real function on this configuration space. And the main assumption of our quantization method is existence of correspondence between points from the configuration space and some projection operator, so something which belongs to the Hilbert space. And we can interpret this projection operator as something which represents this particular points on the Hilbert space. And finding the counterpart, the quantum counterpart of classical observable can be done by taking this projection operator, which corresponds to some point, next integrated by a value of observable in this particular point, and integrated over the full configuration space. The next point in our motivation list is a problem of quantization of time variable. So in our quantization method, we would like to transfer this equivalence treatment of time and coordinates, which is based on relativistic physics, also to this quantum picture. And because of that, we forced to analyze the operator of position in time in exactly the same way as it is for operation of position in space. And as you will see, in our quantization method, it's very simple to construct such operator. And the last problem is analysis of quantum analysis of gravitational singularity. And during my talk, I will propose some idea how to go through this problem. And I will also give you an example of such a analysis in the case of Oppenheimer-Snyder black hole. Okay, this is the plan of my presentation, but it's not so much important. Let's start from the structure of affine group. So our quantization method will be based on the affine group. Here you can see the parameterization of affine group is done by two parameters. The first one is real. The second one is real positive. Here you can see the multiplication law, and we also need some left invariant Haar measure for our purpose. And because of this requirement of quantization, we need correspondence between points from the configuration space and group elements. The simplest way how to find this correspondence is simply to take P as a time, because it's real, and Q as a R, as radial coordinates, because it's real positive. And in my calculation, I will present you, and during this talk, I will take such a correspondence, but it is not the only possibility. Okay, next we need some Hilbert space, which would be our carrier space. So we take it as a square integrable function on a half-line with such a measure. We also need representation of the affine group on this Hilbert space, and it is defined in the following way. And next, we would like to have this correspondence between points from the configuration space and some object from the Hilbert space. And we are doing it in the following way. We choose some vector from the Hilbert space. It's arbitrary vector but it must fulfill some conditions, right? And it's called fiducial vector. And next, we transform this vector by every element of the group. So as a result, we get elements from the Hilbert space. They are a function which belongs to the space, our carrier space, but they are parametrized by the elements of the group. So actually, they are parametrized by elements, by points of our configuration space. And the fiducial vector must be, okay, and such states are called the coherent states. And the fiducial vector must be chosen in such a way that the coherent states provides the resolution of unity, and the quantization can be performed in exactly the way I presented you at the introduction. So we build the projection operator, which projects on a subspace spanned by given coherent state. Next, integrate this, multiply this projection operator by value of observable and integrate over full here affine group, but we know that it's actually the configuration space. Okay, so far we know how to build the quantum observable, quantum operator. So now let's go to the problem of analysis of gravitational singularity. And this is our proposition how to deal with such a problem. And in classical physics, the gravitational singularities signalized, existence of gravitational singularities is signalized by blow-up of curvature invariance. And we would like to construct the condition which would be, which will use the quantum language, but which corresponds to such a classical interpretation. So let me start from the subset of observables, namely the curvature invariance. After our quantization, we get the set of quantum observables, quantum operators, and we will say that the state psi, that the quantum gravitational singularity in the state psi exists or is reached if this two condition is true. The first one says that the expectation value of curvature invariance in state psi goes to infinity. It is something which comes from the classical interpretation. We simply replace the observable by expectation value. The second condition says that the variance of the curvature invariance in state psi must go to zero. It is something which comes from our quantum aspects of our model, and it can be interpreted in such a way that the state is well localized inside the gravitational singularity, and the probability of finding the state outside the gravitational singularity is equal to zero. Okay, so now let's go to the description of our model. So the classical description of Oppenheimer-Snyder model based on a following paper. In this paper, they were analyzed the LTB model of spherical symmetric perfect fluid in the Pędrak coordinates. Here you can see the metric in these coordinates. T and R are time and radial coordinates. And the advantage of this method is that time is always time-like and T is always space-like. Alpha is a lapse function. We have also function E, which measures the energy of a shell at the radius r, and we also have a mass function, which is defined in the following way. Okay, here you can see the equation, field equation. It's something which we write actually from this paper, so it is maybe not so much important for us. In our case, we would like to analyze the dust case. So the pressureless dust case, we take P equal to 0 and alpha equal to 1. The equation, the field equation has the following form under such a condition. Moreover, we also take E equal to 0. So we got so-called marginally bound model in this case. And the field equation reduced to the first one, which looks in the following way and which can be solved analytically. Okay, we get following mass profile, where lambda and C1 are real parameters, and dependence on these two parameters can be reduced actually to dependence on one parameter, which is equal, here is a misprint, it should be C1 over lambda, not lambda over C1. And the form of this mass profile is as follows. Okay, for us the most interesting part is of course the curvature invariants, and in this model they have the following form. They can be reduced, the form of this curvature invariant can be reduced or rewrite in the following way by using so-called, by using epsilon variable, which is defined in the following way. And we see that in all of this curvature scalar, we get this epsilon variable with the negative power, so we get the gravitational singularity if epsilon goes to 0. Epsilon goes to 0 if t goes to minus C1 over lambda. So it is our gravitational singularity in this model. So now let's go to the quantization of this model. We start from the quantization of elementary observables, so quantization of time and quantization of radial coordinates. And you see that the form of this operator are very symmetric. We have no problem with construction of a time operator. And we also would like to analyze the model in which mass is limited. So we would like to cut off the mass profile at some level m0. So for r greater than r0, the mass profile is constant. For r lower than r0, the mass is exactly the same as it was as the one we get from the field equation. The mass operator looks in the following way, and the interesting thing here is that if we choose the wave function in such a way that this first integral is equal to 0, it means that such a state is actually eigenstate for this operator, because it's only the second integral left, and the second integral would give us the identity of the identity operator. So such a state, which is equal to 0 for r lower than r0, are eigenstates of our mass operator with the value m0. And such a states, because we are this consider of black hole evaporation due to the Hawking radiation, such a state will give us the conservation of mass. They will be the state for which the mass conservation is true. Moreover, it is possible to prove that M is a bounded operator. Okay. Now we would like to quantize our curvature invariance, and this problem can be generalized by introducing the following function, which depends on alpha, beta, and gamma. And by using this function, it is possible to rewrite the curvature invariance as some linear combination of a function with different parameters. So we can reduce the problem of analysis the curvature scalars to analysis the operator of A, this function A. Okay, so because of our proposition of analysis of gravitational singularity, we would like to analyze this gravitational singularity by analyzing the expectation value and the variance. So to do that, we need some set of functions, right? Because we have to compute this expectation value and the variance in some state. We also want to have assured that we are analyzing some particular area of behaving of our we would like to analyze the behavior of our observable in some particular area. And the best way to provide this is simply to choose the wave function as a function with compact support. And we actually do that. Here you can see the function, which depends on two parameters, eta1 and eta2. And it is a function which is actually kind of step function. He is a characteristic function, So R is a function which is described, which is defined by such a formula, and it represents the radius of a shell with the mass y and time x. And this characteristic function limits the support in the R dimension. This characteristic function limits the support in t dimension, and we also have such an object which also which provides that this wave function is equal to 0 in a neighborhood of gravitational singularity with the radius epsilon half. Okay, so it is interesting to look how exactly the support looks like. Okay, so here you can see the support is represented by this blue area. These two blue lines represents the shell with mass eta 1 and eta 1 plus delta 1, and it comes from this part of our wave function. This dashed line limits the support in the time dimension, and this gray part, this gray area, is an area in which the function must be equal to 0. Okay, so the support can be shifted very close to the gravitational singularity, this vertical red line, but in this blue area it will be equal to 0 because of this last part of our wave function. Of course, we can control the radius of this gray area, and in a limit we can take that this radius is equal to 0. Okay, so now let us analyze the expectation value of operators of observables in this particular family of a wave function. So expectation value of elementary observables are well defined. It is for sure well defined because this function possesses a compact support. Moreover, when delta 1 and delta 2 are small, we can say that the expectation value of t is equal to eta 2, so which is in the middle of this period. And it seems to be natural because if we take eta 2 very small, it reduces to something which is placed exactly in the middle of this period. The expectation value of R is equal to such a formula, and it is placed in exactly in this lower gray line, lower blue line, between this dashed line, exactly in the middle, and it also seems to be natural because when we take delta 1 very small, this upper blue line lies very close to the lower, and it's placed exactly in the middle of this period. So we can conclude that actually this expectation value gives us quite good localization of this wave function. When we calculate the expectation value of mass operator for state for which eta 1 is greater than m0, it turns out that this expectation value is equal to m0. Moreover, such a function are eigenfunction of mass operator, and such a function are placed above this red area. Okay, so such a function are something here, somewhere here. Okay, but the most interesting part for us is the analysis of curvature invariance, right? So it turns out that if we keep epsilon greater than 0, the expectation value is limited, but when we take epsilon, the limit epsilon going to 0, it turns out that the expectation value goes to infinity. Okay, so we can conclude here that the expectation value of these operators in state psi contain the singularity diverge. So it is something. So this property fulfills this first condition of our gravitational singularity analysis. So such a function with epsilon going to 0 are good candidates to be a state in which gravitational singularity achieve. So let's go to the second condition. Let's analyze the variance of this operator A. And before I make some statement, let me give you some general consideration. So because of A operator is symmetric, this comes from the method of quantization, and if epsilon is greater than 0, it turns out that the variance can be rewrite as a norm of some vector. Okay, square of the norm actually. So the variance must be positive or equal to 0, and is equal to 0 only if the vector inside here is a 0 vector. But this vector would be a 0 vector if and only if function vector psi fulfill the eigenequation of A operator. So in such a case, the function psi must be eigenstates for operator A. And it turns out that in our family of functions, there is no eigenstates of A operator for any epsilon. What's the conclusion? We can say that the expectation value of the operator corresponding to the scalar invariance are singular because of this blow-upping expectation value, but those singularities occur with non-zero fluctuation. So it means that the possibility of finding the state outside the singularity is non-zero. Okay, so now let's go to some other interesting facts which comes from our model. The first interesting fact is an analysis of expectation value of radial coordinates as a function of eta2. So we fix eta1. Let me remind you that eta1 represents the mass of the shell. So we fix mass of the shell, we treat it as a function of eta2, and it turns out that such a function possesses a minimum, and this minimum is exactly at eta2 equal to Tc, so equal to the time in which we get this gravitational singularity in classical picture. And here you can see the picture of the plot of this function for different eta1. The lowest line, the blue line, represents this function for eta1 equal the lowest possible, so equal to m0. And we actually see that here we got the minimum, but on the other side of this singularity, we see that the plot is symmetric. So we can conclude that after that the radius we get, this minimal radius, represents the bouncing radius of the Oppenheimer-Snyder star, and after the bounce, the quantum star expands. This picture are symmetric. For a larger eta1, we get that these plots are shifted or placed a little bit higher, right? So the vertical position of this minimum is a little bit higher, but we still see exactly the same behavior, so we see this symmetric picture. Okay, and one more interesting fact, namely the position of the horizon in our model. So we start from the equation of the position of the horizon, but rewrite in a quantum language. Okay, so we replace the observable by expectation value. And it's worth to note that this equation is well defined even near the gravitational singularity. It is because the mass operator is bounded. So it can be solved. It can be solved, and it turns out that we get two solutions of this equation. Okay, the solutions are approximately equal to such things. And the first solution corresponds to classical horizon. But we also get the second solution, which is placed symmetrically with respect to the position of the gravitational singularity. And this is our hypothesis that it may describe the closure of the horizon. Okay, so now let's go to the conclusion. During my talk, I presented you the quantum evolution of Oppenheimer-Snyder star. We see that our star collapses. We see the strong quantum regime in which we have the singularity smearing, right? This variance of the curvature invariants were non-zero. And we also see that we have bones of the Oppenheimer-Snyder star. The quantum Oppenheimer-Snyder black hole possesses also the horizon. We see also two horizons, the position of two horizons. And we say that probably, maybe, the second horizon may correspond to the disappearance of the first one. And I also present you the quantization of time, observable, and you see that it could lead to the consistent quantum theory. Okay, so thank you very much.
Thank you. Yes, you read.
So I have many questions on many levels. I don't know whether to start from the surface or whether to start from the bottom. I understand that the scheme of this theory is that we have some algorithm to turn a function into an operator
Yes.
in some Hilbert space, and then we take solution to Einstein equations. Our function is a complement of the metric tensor or curvature or whatever we choose, whatever tensor we choose, and then using this algorithm we turn it into operator, and once we have operator then we do the usual quantum mechanical operations. So it means that there coexist two theories. There is this exact classical theory as one ingredient, and then this quantum theory derived from the classical theory.
Yes, we can say
Yeah,
that.
so I didn't understand in what way, for instance, you obtain this bounce, while in classical theory nothing bounces.
Yes, so maybe mathematically, what is the position? Okay.
Yes, this is a technical question.
Yes, I understand. Okay, so firstly, let's notice that mass operator, or this is a classical mass function, is symmetric with respect to the t, with respect to this tc, right? When we change in this place.
Okay, so this bounce is already in the classical function.
Yes, but we define it not only on a time lower than tc, but also in a place where t is greater than tc. So it's something which we put inside our model. This is first part. The second part, our wave function we are considering are also symmetric with respect to tc, because we are considering the part which is in time lower than tc, and also the part which is greater than tc. So we get the bones, but it comes from the symmetry of our model. It is also possible to get the results we are talking about, that in this other part for tc, for t greater than tc, do not have the second part, simply by assuming that our wave function at this part is equal to 0. And we get it, right? We get it. But what the thing I want you to show is the possibility of this model. Okay, we have symmetry when the symmetry of the operator. When we put the symmetry of the wave function, we see that after the gravitational singularity, we got something.
Okay, so this in this classical part, this function is just free. I can set it in arbitrary way. Yes.
In classical we do not have wave function, right?
No, I
We
mean
do
this
not know what
function
happens.
this function m of t and r.
Yes.
So this I mean by the solution. So it means this is not vacuum solution. This is solution with some stress energy. Is that? But is it the property of classical solutions that this dust bounces instead of collapsing?
Well, it is property of this solution. Yeah. But in classical analysis, the space-time finished at this DC. Okay.
It's problem of interpretation. If you cut the space-time, the singularity is a finish of a motion.
Oh, I see. So your bounce is. I understand. So your bounce includes singularity in the middle, this classical solution, and then you replace it by some quantum solution in which the singularity is smoothed out.
Yes.
Okay, thank you. I understand. Yeah, I have other questions, but I have
Okay. Are there any other questions? Yes.
This is probably another. Why do we start with a affine group? Can I choose a different one?
Yes, but we choose the affine group because of it suits very well to this space-time, right? Our space-time, this actually not space-time, but configuration space consists time and radial coordinates, and the affine group suits.
So I understand that in a more complicated case, I would have to search for another.
Yes, of course.
Okay, so let us end this meeting.